Okay, now let's go to our original example circuit and see what are different options that we do have here for our transfer function. In this circuit, we have only one input, and that's VG, so we don't have more than one choice for our input, but we can choose different output for our transfer function. So for example, we can focus on the voltage of capacitor, which is VC, or we can focus on the voltage of inductor, or the current of 250 ohm resistor, which is the same as IL. So these are different parameters that I can consider as the output of my transfer function. So if I choose to work with the voltage of capacitor, then I have a transfer function that I'm going to call it as H1. So H1 of S has VC as output, and the input is VG of S. Then I can work with another transfer function which has the voltage of inductor as my output, and still the input is VG of S, or for example H3 of S, which is focusing on the current of inductor, and again my input is VG of S. So you can see that I can define a bunch of different transfer function for one particular circuit. So you can choose any parameter of interest to be your output signal, and you can choose among your input to focus on the effect of that particular input. So here, because I have only one input, then the input signal for all these different transfer functions are the same as VG of S, but the output signal is selected in a different way. Okay, now let's focus on, for example, H1 of S and see what is this transfer function. H1 of S is focusing on the voltage of capacitor, or basically the voltage of this parallel component, with respect to the voltage of my input. The way that you have to solve is that you have to consider your input with general term, and then try to solve, and at the end try to get the relationship out. So I'm going to start with solving for VC of S, which is my output signal. So in order to describe VC of S, the first thing I need to have is the equivalent impedance between these two branches, because the voltage is still the same for their equivalent. And then if I have the equivalent, I'll be able to describe my current. Now, what the voltage, this equivalent impedance, if I call it as Z equivalent, is equal to, let's call this impedance as Z1 and this one as Z2. So the equivalent impedance is going to be Z1 multiplied by Z2 over Z1 plus Z2. So what I have for Z1 is basically 1 over CS, and that's equal to 10 to 6 over S. And here for inductor, I need to have LS. So what I need to do is that I have to add S in front of 0.05. Now let's find Z equivalent here. My Z equivalent is going to be Z1 multiplied by Z2. Z1 is 10 to 6 over S multiplied by Z2, which is 250 plus 0.05 S, and then in denominator I have to add everything together. So 250 plus 0.05 S plus 10 to 6 over S. If I multiply both numerator and denominator by 20 S and rearrange everything, I'm going to have 10 to 6 S plus 5,000, and in denominator I'm going to have S squared plus 5,000 S plus 20 multiplied by 10 to 6. Now that I have my Z equivalent, I can redraw my circuit in this form. So here I have my VG. There is a 1000 ohm resistor here, and then it is connected to my Z equivalent. And the voltage of capacitor is the same as the voltage of Z equivalent. So if I'm looking for the voltage of capacitor, what I have to do is that I have to do a voltage divider. So it tells me that VC is equal to Z equivalent over Z equivalent multiplied by, plus 1000. So the impedance of this component over the whole impedance, which is all here. So Z equivalent over Z equivalent plus 1000 multiplied by the total voltage, which is VG. Now I have my Z equivalent. If I replace Z equivalent in this equation, I'm going to have VC of S as 1000 multiplied by S plus 5000 over S squared plus 6000 S plus 25 multiplied by 10 to 6 multiplied by VG of S. So as you can see, because I was trying to keep my VG of S in general form, so I was not describing VG of S in terms of mathematical function, then at the end what I have for VC of S is a coefficient or a fraction multiplied by VG of S. Now at this time, at this point, what I can do is that I can describe the relationship between VC of S over VG of S, and I can find my transfer function. So what I'm going to do is that instead of writing this equation in this form, I'm going to delete this VG. I'll bring it to the other side. So here I'm going to have VC of S over VG of S, and that's what I'm calling as my H1. So my transfer function, which is H1 of S, is equal to what I have here. So I found my transfer function that describe the relationship between the output voltage, which here is VC, to the input source voltage, which is VG of S in Laplace domain.